Yeah, so we just learned about transfer learning and that it can be useful to leverage pre-trained models. So let's now see how transfer learning works in practice. We will start with a simple baseline, a ResNet that has been trained without transfer learning, and then we will compare this ResNet with two variants where we use transfer learning.
Yeah, as it is best practice, we will again start with a baseline. And here, this is the code that we used already in Unit 7.5. So this is the ResNet 18 notebook where we are training a ResNet 18 that we load from the Torch Vision Hub here. So we are training it on Cypher 10 images. And yeah, we get, if I scroll to the bottom, we get 84.3% accuracy. So I'm not going to run this notebook again because it takes quite some time, but we are now going to modify this notebook to explore transfer learning. So here I made a copy of that notebook and then we are going to modify it. Let me clear all the outputs and then we are going to train this notebook using transfer learning. But let me show you first the modifications we are going to make. Yeah, let me first change this part here. So before we just loaded a ResNet 18 architecture and now we are loading a pre-trained ResNet 18 model. So we are going to change weights here from none to the pre-trained weights. So it happened that someone trained this on ImageNet with 1000 classes. So the correct reference here, and I will show you a link later where you can find this information. The correct reference here is ImageNet 1K_ version 1. And this will now load a ResNet 18 with pre-trained weights where someone pre-trained this network. So let's load this code here. So now we have a pre-trained ResNet 18 here. We are now going to modify this because this is a network trained on ImageNet on 1000 classes, and we want to adjust it to our target dataset, the Cypher 10 dataset. And by the way, there's also an alternative way of using these weights. So you can alternatively also import the model ResNet 18 directly from Torch Vision models, and then also load the corresponding weights and then access them via this attribute here. So this is just an alternative way. If this one, for example, doesn't work for you, you can also use this alternative here. But getting back to the model, now we have this ResNet 18 with the weights here, which is for the 1000 classes. And now we want to adjust this for our Cypher 10 dataset. So in order to find out how we can change this network so that the last layer of this network matches, let's say, our 10 class classification task in Cypher 10, it is always helpful to inspect the model first. So I like to just print out the model how it looks like. So I can do PyTorch model, and this will then show me the model architecture in PyTorch. So this is how the model is set up. So we can see we have these basic blocks, the sequential, and so forth. So that's basically similar to how we implemented our ResNet from scratch, except that this is implementation provided by Torch Vision. So if we scroll down to the very bottom here, we can see there is a fully connected layer. This is the output layer. So there are 512 input features here in the output layer and 1000 classes. So we now want to change that to 10 classes, which matches our Cypher 10 dataset. And then we are going to train only the last layer. So we will freeze the whole network and only train the last layer. In the next notebook, in a few moments, I will show you what the results are if we are training the full network. So let's start with training the last layer. So for that, I'm freezing all the parameters first. So what I'm doing is I'm doing for each parameter in our PyTorch model, I'm setting the requires gradient to false. Now everything is frozen, nothing will be updated when we train the model, but we want to update the last layer. So we are swapping out now this layer with our custom layer that we initialize from scratch. So I will say PyTorch_model, and then we want to access this last aspect here, the last fully connected layer. So we say .fc, and then we override that with our own fully connected layer. So we say torch nn.linear. And we have to use the 512 input features because those don't change. But now we only have 10 output classes. One more modification that I recommend is also applying the same data transformations that were used for pre-training that model. So for this case, the authors also provide the transforms that were used. So for that, what we can do is we can do from Torch Vision models. Import ResNet 18. And then the weights. And then let's just access the weights like this. And then we are going to access the transforms. So I do preprocess transform, which we are saving from the weights, but transforms here. So let's just take a look at what they look like, these weights. So let's do preprocess transform to, visualize this. Should be, of course, transform. No. Weights is not defined. Oh, I said weight. Okay, now it works. So we can see, there is some cropping going on here, 224. Then it's a resizing to 256 pixels. And then we have the mean and the standard deviations here. So before we used 0.5 everywhere. Here it's a slightly different number that is derived from that ImageNet dataset. And and then we are going to use those for our Cypher 10 data module. So for example, we would modify this. And we can load this data module. Take a look at the images. So there are now 24 times 24. And then, we are training the model. So here, again, we have to make sure we are applying the transforms. And then we can train the model. So that might take a while. So let's now take a look at the results. As we can see, the loss goes down at first, but then it tends to fluctuate around a constant value here. So at some point the network doesn't really learn anything, and that's maybe because we are only updating the last layer. And then looking at the training accuracy and validation set accuracy, it also doesn't look great. So we only get 75% accuracy. So this might be because we are only training the last layer. And in this case, it's maybe not sufficient. Maybe we have to train more layers. So I will now show you how we do that, how we train the whole network. And it's just a slight modification. So I will make a copy of this notebook and then show you the modification. And then we will train this whole network instead of just the last layer. So now we are going to train the whole model instead of only changing and tuning the last layer. So we are going to change the last layer and tune the whole model. So let's clear the outputs here, and then let's look at the modification that we have to make. So essentially everything is the same as before, except of course we don't want to freeze these layers here. So the only thing we have to do here really is commenting out these two lines, and then it will train the whole model. So let's actually see how that helps, if it can help improving the performance. And the first thing we can notice here is that the loss is already much lower than we had it before. However, we may have actually trained for too long. It was quite wasteful. We can see after epoch 10, there's nothing really happening here. And the same is true for the accuracy here. So when we look at the training and validation accuracy, it saturates after epoch 10, but the performance is much better now. We can see we get about 95% accuracy here. And if we scroll down to the test accuracy, we get 95% test accuracy. So this is actually a great model. We only trained for, let's say, a few epochs using this pre-trained model, and it performs much better than our from scratch implementation when we train the model, let's say, on Cypher 10 without using the pre-trained weights.
So in this video, we saw two different techniques for transfer learning, and comparing it to our baseline, we can see that one of these two methods at least was able to improve the performance by a lot. So in practice, leveraging pre-trained models can be very beneficial.